Okay, I'm back. Got another lunch break free, so let's continue the sorting journey. First up, recap. Where have we got to so far? So we looked at all the sort of different sorts and decided to do a quick sort, but using value for pivots, cooked up like a radix sort. We've implemented that. There's no base case yet. There's no pattern check. But on the plus side, it is doing a pivot, just the one radix value, and it's doing it kind of adaptively. So let's have a look at the benchmarks, see where we've got to there. I don't think the last video quite covered them all. So check it out. So let's just look at the bottom one. The current implementation is the blue. We're just only looking against some pretty basic implementations. These are not vectorized. So we've got a pdqsort, which is the standard Golang one, and a timsort implementation. So that's versus a basic merge and quick sort. No vectorized, no parallel ops. Blue one, fared it slower. I think it's like 10 times slower than pdqsort. If we look at a sort of series of ascending segments, these other ones speed up. Okay, if we look at 20 unique values, and actually it becomes the quickest. This is the best case because there's only 20 values, very few like unique bits are in use, which means that adaptive split is going to work really well. It's just only going to do, if you've got 20 values, and I think it's numbers 0 to 20 here. Is that using for 5 bits? So it'll only have to do like 5 passes through, even without a proper base case catching it. So that shows that we can do better than them. Nice. Really slow when it's reverse sorted. I think both of these just catch that pattern. And same with near sorted. All right, work to do. So today let's just make those basic improvements. Let's get started. So let's do the base case first, shall we? I have got an old insertion base case that was from a video about optimizing code. Multiple implementations trying to refine it. I don't know which is which. Perform the reads, then the writes, that's good. So they're all doing it in order. We're using a copy, which is good as well. This is trying to prevent bounce checks. I mean, I guess number 4 is fine. Oh, and then we've got loop unraveling, which reads 4 things into memory, sorts, continues. Oh, it's a tough choice. This will be the quickest. So no longer insertion sort 6. Yeah, that name exists, no surprise. Just deciding whether or not we should expose it so we can test it or not. It's tested in its other form. Data's a numeric. We're changing that now to being an int. Yep, that's good. Less than or equal to 1 could be. Yeah, that's right. I think it was 0 before. So, that means it's sorted. $32. Yeah, okay, 32. That's the recursive call. And then we also have to do it in the loop, don't we? Yeah, it's the same base case. It's about how the recursion ends. Yep, it's all right. Bit rusty. Okay, so that looks fine. We can probably run those benchmarks. We've got deterministic ascending segments. It is pretty close to pdqsort, but again, looking similar to the random ones, it's just a bit slower. Yeah, interesting. And for sorting the unique values, it is still better, but actually, they actually got fractionally worse, and that's probably because insertion sort is not as good as just dealing with those last couple of pivots and quickly realizing that everything is the same value and quitting out. So yeah, maybe we could do an extra check there to check if like there's only 1 radix left, keep going as well. Like there's another form of early termination. Interesting. Let's take a beat. Let's pick up the code. So I'm actually thinking that we've done a sort of partition the outside and in. There's the extra check. high-low will be less than or equal to 1 if the values are all the same. Yeah, so that's if you get all the way down to no significant bits. All right, if you're down to 2, it feels like maybe don't do the insertion sort here. But unfortunately, the other check is later, after generating the pivot value. Could change that. Got another thought as well about this base case. So we've done an insertion sort. It's nice. It's fairly quick. The other way of doing a base case, actually, the other way that's standard, and the vectorized ones, is using a sorting network, which basically decides ahead of time exactly what comparisons are going to be done, and always does the same ones. Your fixed length of data sorted. And that's really good for doing parallel processing. It's great for GPUs, because there's no context. You're always doing the same operations, so you can just optimize things a whole lot there. So that's one thing. I don't know if we'll go there. Maybe that's an alternative. But the other thought is that we're doing quicksort, and so when we get to a base case, it's fine. You can get it sorted and you're done. But if we let everything go to the base cases, you'd have a full array. So let's say you've got to your base case, let's say less than 32 length, and just stopped. So you have these unsorted chunks, but relative to one another, each chunk is in the correct order. So that means you could then do a sort of a bottom-up, a very short amount of a bottom-up sort at the end of it. So rather than doing one little base case and another one, scattered around whenever you hit them, doing your full recursion, like quicksort, and then doing one pass through or a few passes through just to tidy up the individual chunks. So you could do that with like a bubble sort. You just have to bubble 32 times and it will be sorted. Like you've got a limit, which is much smaller than if you try to bubble sort on a billion values. We're doing a shell sort, which is probably a bit nicer for doing it in parallel. Shell sort is bubble sort, but you do all the evens. At least I think this is what shell sort does. If it's not, then it should be. You could do a bubble sort where you do all the evens, then you do all the odds, and they'll still bubble eventually with the same amount. But each of those individual comparisons are independent. So you could find the min-max, sort these two, sort the next two, sort the next two with no dependencies. This one can be done in parallel with the next, and so on. And then you shuffle up by one and do all the odds, and so on. That could be a nice way of doing it too. So anyway, thoughts. Something people haven't done is the recursion, halt it early, and then do a whole separate tidy up after the initial sort. Okay, what's the downside of that? The downside is you're basically sorting networks which have a fixed cost, and other people are probably going to optimize them better than me. So do I want to go down that route and really get nasty? If I go to GPU sorting, it kind of makes sense. I don't know if I want to go there. If I'm doing insertion sort, it does comparisons, and so it can terminate early. It can say, I've found the spot it belongs in an already sorted array, it's always near the end, and it's really quick and efficient. So instead, I think what I prefer is doing a lot of extra work at these early bits with the pivot, generating the pivot value. Generating the pivot value where we check out what's going on and try and make it as close to that good insertion sort base case as possible. And that's the spot where last video I talked about trying to keep things ascending by deciding whether you work inside out for your swaps or in order. Because if we can keep them all in order, I think that should more often be a good case for insertion sort. Maybe we can do better than the sorting networks. Anyway, next up is patterns. I didn't look at the benchmark for the reversing because I knew it would be rubbish. So we're still worse than pdqsort. Let's add a reverse check. We can do it in here. And what we're going to do is just count greater thans. No. Wait, do we want to do an increment? Is that okay? Increment you have to read and write. It's going to be in a register. It'll be fine. If v is greater than I, ground truth plus plus. Yeah. 2 reads. Prev is going to be equal to data 0. And this way we can just do it with prev. And prev is equal to v. That is nicer. We have to return a bit more, right? So we're going to return the pivot. Do we just do a boolean for how many let's just return the int, which is number of sorted. I think in the future, if we do multiple passes in here, it won't just be generating a pivot value. We're going to generate a whole bunch of stuff, important stats. So let's just get used to passing more information out of that function. So if we have generate, the whole test is going to fail now as well. It's all right. Truth count. Pivot value is 0, you can return. Pardon me. If the ground truth count, how many are going upwards, is equal to 0, reverse. Let's just make the function call. It's going to be fast reverse. Nice. Data low high. Yep, I'm happy with that. Reverse, correct. Doesn't look very fast. It is doing all the way up. That means you... What? Yeah, divide by 2. Okay, you know what? Let's get rid of the low high. Let's just reverse a slice because that's going to be way nicer. Yeah. So that means we can go from 0 to half the length. That gets cleared from the length. So a fast reverse probably should be reading in multiple until you get close to the center. That way you don't do all the writes. Yep, let's do it fast. We've got time. My lunch break is just beginning still. Data I. Let's just do V1. Come on, is that enough of a hint? Do you know what I'm doing now? Okay, let's just say, you know what? Just make a copy of what we just did. We're going to start with I on the outside, so we don't have to do that. And then we do for I is less than length of data divided by 2 minus however many we're loading. Let's just do four on each side. So we want the low ones and the high. We'll load 4. I'm getting 4 ready because 64 bits times 4 is going to be 256, and this old machine can only do AVX 256. So when we come to doing parallelization, I'm not going to do AVX 512 unless I can afford a new CPU, and I can't. Yeah, well, no, that one's I+2. You're on the right. You normally like spaces because you're Golang. Correct. That's more like it. We don't need any ifs. This is not conditional. We do a large read. We do a large... Oh! No. I was thinking we could do some fancy copy thing. I don't think there's any reversibles in the copying. And write a bunch. It's going to be equal to high 4. No, it's going to be equal to high 1. Yes, because it's a minus. Aha. AI1, me 0. I goes up by 4. Yep, we could probably just do it. Yeah, this looks, I think it's more readable. I minus 1 is low. 1, 2, 3, 4. Yep. And then we just do a regular sort all the way up. So this is the remainder. Just do it in a non-parallel way. So, okay, we've got one error, and then we have to do a unit test for the reverse. Oh, there, return 0, pivot value. Sure. There are none that ascend. Okay, it passed. Right, now let's test. Fast reverse is not exported. Can I do? Yeah, what's my package? Numeric sort test. Yeah, okay, so this is what happened last time as well. Should your test, if it's testable, export it, I guess. Let's see, you should just be using search. Sorry, Vim. Good. Let's test the reverse. That's a bit short. I like that it's out of order so you can just check that it's sorted. No, we need to test the quick part as well. So ascending range from 50 to 100. That'll do a few passes. It's not a multiple of 4. 50. It's going to be off. Yeah, that's good. And we can run you. Fail. I is 0, less than 50, 50 plus I. That's not us. Oh. It is ascending. I wanted descending. Let's just write this. I meant descending. Can you work it out? Yes, 100 minus. Good. That works. Great. Have we used it in the sort? We did. We reversed it there. Guess that's it. Let's do the benchmark. Tunnel. Benchmark. Right, what have we got to? So I think we made a slight decrease in our standard sort here, and even the best case. We are still slightly better than the PDQ sort, but not by much. It's the extra overhead during that first scan finding the pivot. Reverse sorted, we are fractionally slower than PDQ sort, which is also disappointing. Again, I'm assuming that's then the cost of the full pass through. Why would I assume that? Why is that slower than what PDQ sort's doing? Suspect. And finally, when it's near sorted, whoa, it gets really bad. Wait, that's normal, right? It's normally going ascending from like sort of 25 to 100 on random values. Yeah, it's going from 10 to 40, so it's fine. All right, let's see what we can do next. So I can either start looking at the individual ops, try and get that pass quicker before we do something fancy, or I could do some other checks for insorted. Yeah. We're not finishing early, because right now we break early if it's all the same value, because our pivot has said there are no suitable bits to split by. We're not doing anything about when it's in order. It's in order when it's the length minus 1. All right, let's add it in. It's going to be same place we check reverse. Here, fast reverse. So if the pivot value is 0, or the ground truth count is not 0, it's equal to high minus low minus 1 minus 2. Wait. If low were all the way from low to low plus 1, for example, that means there's an element, one element. And there should be 0 of these. It's just subtracting 1. There would be 0 of them. Yeah. Okay, so that could make a big difference. Benchmark. All right, where have we got to? On random values, still not substantially different. Maybe I think it just regained what we lost from adding the extra checks in the first pass through. Looks like ascending segments we improved slightly, but still not as good as PDQ sort, SAG. Sorting 20 unique values, still the fastest once you get to any reasonable size length. Reverse sort, we are still slightly slower than PDQ sort. That's also sad. I would like to be doing quicker than that. And near sorted with this one swap, we're now the fastest, so that check for being in order is like somehow made us way quicker than the alternatives.